Hi. Tonight I'm here with Dr. Gibor Bari, professor at the University of California at Berkeley, among other things. Dr. Bari, just to kick off, tell us a bit about the Kepler mission, what it's supposed to do, what stage it's at now.
The Kepler mission was a gleam in Bill Baruchi's eye 25 years ago, before we even knew that there were planets around other stars. So the basic mission is intended to tell us what is the frequency of planets around other stars, and in particular, what is the frequency of rocky planets, or planets like our own, terrestrial planets. So once the planets were beginning to be discovered around other stars, we mostly were finding large planets like Jupiter. And they used a different technique of finding planets than the Kepler mission does. So Kepler was still a very interesting idea, and NASA finally picked it up in order to find smaller planets. And so now we are finding really thousands of candidate stars with planets around them. And it's telling us what nature likes to make by way of planets and how many stars might have them.
Wow, that's amazing. So the title of your presentation, I think, is Hunt for Earth 2, and is perhaps once you identify these, does it identify atmosphere and other things as you know?
Yeah. So the Hunt for Earth 2 is kind of the hook. Really, as scientists and astrophysicists, what we want to know is the frequency of solar systems. We want to know the distribution of planet sizes, the distribution of orbital distances, and so on. It would be really great if we found a planet that was the same size as the Earth around a star just like the Sun in the same orbital period. So the experiment is designed that it could, in principle, find such a planet. But as a scientist, I'd really say that it's really more about what is the assay of planets, and it'll tell us even if you don't find Earth 2. If you find a lot of Earth-sized planets, at various distances from their stars, and they're pretty common, that Earth 2 is out there. And the larger the frequency of the planets is, the more likely that one like the Earth is close to us. If they were rare, then it'd probably be far away.
Okay. And this is moving now. I guess, how is it still within our solar system? Where's it headed for?
So Kepler is a telescope. And it's not on the Earth, and it's not in Earth orbit just because we need a really quiet environment to do the experiment that we need to do. So it's essentially tagging along behind the Earth and slowly falling behind. So it's in a solar orbit very much like the Earth's, and it's about a quarter of the way back now after 4 years. And so it's just orbiting the Sun like the Earth does, and it's just getting a little further from the Earth.
How does this differ from something like the Hubble Telescope? I mean, they're looking for different things. So,
so Hubble is in Earth orbit. It's in low Earth orbit, actually. So it undergoes, it goes into the Earth's shadow, every 90 minutes, and it has a lot of changes that take place that would make it hard to do the same experiment that Kepler's doing. Hubble is also, it's got a very small field of view, has exquisite resolution, so it gets very detailed pictures of a very tiny piece of the sky. Kepler looks at a much larger piece of the sky and doesn't care about the picture. It's just measuring the brightness of stars. So essentially we get a much lousier picture of a much bigger piece of the sky, but it gives us the data that we need to detect planets.
what technique does the Kepler technology telescope use to detect these exoplanets? Is that the right word?
Exoplanets is a good word, yeah. It's actually a really simple technique. It's called transits. Some of the viewers will have remembered that there was a transit of Venus last year. So that just meant that Venus came between us and the Sun, and we saw Venus as a little black dot crossing the Sun for a few hours. That's the same technique that Kepler uses. The only thing is that all the stars are very far away, so they're all points of light. So you don't see a disk of the star and then a planet crossing in front of it. You just see the star, but when a planet's crossing in front of it, it's blocking a little bit of light. And so what we really do is we just measure the brightness of stars to exquisite accuracy, And when a planet crosses in front of them, there's a little dip in the brightness of the star while the planet's crossing, and then it's gone again. The planet goes all the way around, comes back, and then the same thing happens. And so what we're really looking for is a periodic dimming of the star, which lasts an appropriate amount of time and has an appropriate depth to be a planet, that repeats in a very periodic way, so that we know that there's a planet orbiting the star.
And you'd like that to be, I mean, it's unlikely it'll be the same, 365 days around whatever star.
Right? So we'll know whatever the orbital period is, so just by how often it repeats. Obviously, it's easier to find planets that repeat more often. You don't have to look as long, right. and you get more instances of it. So Kepler is particularly sensitive to planets that are close to their stars, and so they have short orbital periods. And of course, the bigger the planet is, the more light it blocks, so that makes it easier to see. So we're more sensitive to larger planets. So that's the basic technique. And if the planetary system has several planets and they're all lined up in a plane, then they may all go across the star. And in fact, we do have systems of up to 6 planets that cross, of course, at different orbital periods and with different depths, because they're different planets in different orbits. Now, most stars they may have planets, but the planets will not be oriented so that the planet actually crosses in front of the star as seen by us. So we won't see any of those. But we know how to correct for that incompleteness. So you can figure out what the geometrical likelihood of a planet crossing in front of a star is, depending on how far it is from the star and how big the star is. And so when we see a planet, we say, okay, we see that one. All the other ones like that, that would be oriented differently, we don't see, but we know what the correction factor is. So you may get to multiply, if you saw a planet like the Earth, for example, the odds that that's going to be lined up is only about 0.5%. So every time you see a planet that's just like the Earth, you could say, I get to multiply by 200, okay. Because I know that I'm only getting 0.5% of them.
Okay, all right. And these are light years away. I mean,
yes.
This can see out quite a ways, right?
So we need the star to be bright enough that the fluctuations in its light, just because of the size of the telescope and the brightness, don't swamp the signal from the planet. And what that does is it limits Kepler to stars that are within a couple thousand light years of here. So we pick out about 150,000 stars in the field of view that Kepler looks at, and we say we're going to study those. And those are the ones that we keep watching. And so we don't actually, basically Kepler is just a giant digital camera. It's about a yard across, and it has a 98 megapixel CCD in it. And then we only choose the pixels that are on stars that are bright enough and the right kind of star, and just download those. And we do that every half hour. So it's a really boring experiment in that sense. It has this not that great picture, and you download the pieces that you want, and it's the same picture all the time. The reason for that is you have no idea which stars are going to have planets that are lined up, and you have no idea when they're going to cross in front of their stars either. So you really need to be looking all the time at the same stars, otherwise you'll miss stuff.
And I would imagine that you have algorithms that just go through and look for this, right? There's not some poor person who's actually...
A computer is looking for this. So we're looking for a periodic signal. So essentially what the computer does is it takes the history of the star's brightness, which of course keeps getting longer, so you keep redoing it, and then it folds that on different time periods and says, if I fold this, do I get an enhanced dip? Every time I fold over at the right period, I'm going to get a better and better signal on the dip due to the planet. So it tries all the different periods all the time, and when it sees something that's significant, it alerts the astronomers, and then they'll go look at it themselves and make sure and do various other tests.
Let's switch just for a moment. You're an expert on the formation of stars, the formation of planets. Excuse me. How is that going to fit?
Very related.
They are? Okay.
Yes. So it turns out, and this is something we learned over the last 30 years or so, that in making a star, it's very hard to avoid getting a big disk of gas and dust around that star, a flattened disk. And we've known for a long time our solar system, all the planets are more or less in the same plane, and they all go in the same direction. which said that probably these formed in a big disk around our sun. Now we can actually see these disks around other stars, and we're even getting to the point where we can see planets forming in them. So that told us before Kepler came along, or the other exoplanet searches, that it seemed increasingly likely to us that planets are reasonably common, because the conditions for making planets seem to be a natural consequence of star formation. And now that's basically being confirmed.
Fascinating. Excellent. I look forward to your lecture. Dr. Bosri is going to, this is part of the Linus Pauling Memorial Lecture Series within the Institute for Science, Engineering, and Public Policy. Thank you again.